Space appears empty to the eye, a black ocean punctuated by stars. But beneath that stillness lies a universe of motion. Planets orbit stars, moons swing around planets, and artificial satellites trace invisible loops through gravitational landscapes. Every orbit, every trajectory, is a negotiation between motion and pull, a balance struck between moving forward and falling inward. It's a celestial dance, choreographed by gravity itself. But every so often, in that intricate ballet, a curious phenomenon occurs. Places where the push and pull cancel out, where an object can hover, seemingly suspended in place. These are the Lagrange points, rare, mathematical eddies in space where satellites can rest without falling, drift without spiraling, and observe without obstruction. These points aren't planets or moons or even objects. They are coordinates, locations where gravity and orbital motion perfectly counterbalance. And yet, they've become some of the most strategically important places in space. Today, our most advanced solar observatories live there. Our deepest space telescopes wait there in silence. Future missions to Mars, the Moon, and beyond may pass through them like ports on a galactic trade route. They are anchors in the void, not because they hold mass, but because they hold possibility. First predicted more than 2 centuries ago by a mathematician armed with no telescope, no spacecraft, and no supercomputer, only the elegance of equations. Lagrange points have become the scaffolding on which humanity is building its future in space. To understand why Lagrange points exist, we must first accept a profound truth. Space is a battlefield of competing forces. Every object with mass, from a tiny moon to a blazing star, exerts gravitational influence. And when two large bodies orbit one another, like the Earth and the Sun, they generate a shared field of force. In most places, a third object, like a spacecraft, will be caught between them, tugged this way and that, requiring constant propulsion to stay put. But Lagrange discovered something extraordinary. In very specific spots, a third object can find perfect balance. It will orbit the Sun in lockstep with Earth, never falling ahead or behind, never drifting away. These aren't stable by chance. They are stable because of deep, underlying symmetries in the laws of motion. These points, 5 in total, are now known as L1 through L5. 3 of them lie along the straight line between the 2 primary masses. These are L1, L2, and L3, spots of equilibrium where gravity's tug is perfectly counteracted by the object's centrifugal motion. The other 2, L4 and L5, sit 60 degrees ahead and behind the smaller body in its orbit, forming a triangle of gravitational harmony. They are the most stable of the 5, and in many planetary systems, they've gathered entire families of asteroids and debris. Perhaps the most famous Lagrange point is L1, located between Earth and the Sun. At about 1.5 million kilometers from Earth, it's close enough to stay in communication, but far enough to offer a constant, uninterrupted view of the Sun. Here, we position solar observatories that guard Earth from space weather. Spacecraft like SOHO and SCAVR live at L1, silently watching the Sun's surface for signs of flares and coronal mass ejections. These solar storms, if directed at Earth, can wreak havoc on satellites, power grids, and communication systems. But by living at L1, these observatories give us critical minutes, even hours, of warning. Enough time to power down vulnerable systems, redirect satellites, and brace for the invisible storm. L1 is not a true parking spot. It's metastable, meaning spacecraft need occasional nudges to stay balanced. But the fuel cost is low, and the benefit is enormous. A solar sentinel always on duty, never blinded by Earth's shadow. On the opposite side of Earth, 1.5 million kilometers farther from the Sun, lies L2. It's a quieter place, darker, colder, and ideal for space telescopes. Because the Earth and Sun always remain in the same direction from this vantage point, spacecraft can use a single heat shield to block out both, maintaining instruments at cryogenic temperatures. This is where the James Webb Space Telescope now resides, a marvel of engineering, unfolding its golden mirrors in perfect darkness, peering billions of years into the past. L2 offers stability, isolation, and line-of-sight communication with Earth. It's the ultimate viewing platform, allowing us to study the faintest galaxies, the oldest stars, and perhaps even the atmospheres of alien worlds. Other future missions will follow. Space agencies envision telescope arrays, gravitational wave detectors, and even quantum communication relays stationed at L2. In this one silent point in space, we may one day observe the birth and death of galaxies, uninterrupted, unseen, undisturbed. L3 sits directly opposite Earth, on the far side of the Sun. It's more theoretical than practical, perpetually hidden and difficult to reach or use. In fiction, L3 has sparked myths of a counter-Earth, a twin planet always out of sight. In reality, it's unstable, and anything placed there would drift away with time. Still, it completes the elegant geometry of the five. L4 and L5, however, are something else entirely. These 2 points are dynamically stable, meaning an object placed there tends to stay there, even when nudged. They act like gravitational basins, places where objects can collect and linger for billions of years. That's why Trojan asteroids orbit at Jupiter's L4 and L5, entire swarms of ancient rocks trapped in gravitational harmony. Earth has a few Trojans of its own, and scientists are eager to study them. Missions like NASA's Lucy are already en route to explore the Jovian Trojans, and future plans may target Earth's, both for science and possible resource mining. In the long future, L4 and L5 may host permanent stations, refueling depots, science labs, or even settlements. Their stability makes them ideal waypoints for interplanetary travel, offering calm seas in the storm of orbital mechanics. Lagrange points are becoming more than just observational platforms. They're becoming nodes in a growing infrastructure of space. Picture a future where communication relays hover at L1, deep space telescopes float at L2, cargo depots rest at L4, and crude habitats swing gently at L5. These locations could serve as natural checkpoints, staging grounds for missions to the Moon, Mars, and beyond. Fuel depots placed at Lagrange points could allow spacecraft to refill mid-journey. Robotic repair drones might be stationed there, ready to service satellites without returning to Earth. Communications satellites at L2 could extend data transmission across the solar system. In time, Lagrange points could form a backbone of interplanetary logistics, tying together Earth, Moon, Mars, and deep space into a connected ecosystem. But it all starts with stability, with the delicate physics that let an object rest, not by resisting motion, but by moving in perfect harmony with it. What makes all this possible isn't just physics, it's insight. Joseph Louis Lagrange, an 18th century mathematician, didn't have a telescope or a rocket. He had only the laws of motion and the tools of mathematics. Yet from that, he derived one of the most elegant solutions in all of orbital mechanics, that in a system of two massive bodies, there exist 5 points where a third object can remain in equilibrium. His discovery went largely unused for centuries, until spaceflight made it suddenly vitally important. Now, hundreds of years later, His equations have given rise to space telescopes, solar sentinels, and future colonies. It's a reminder that profound understanding often begins with questions, not tools, and that deep knowledge can shape the future long before the technology to use it exists. Lagrange points aren't destinations. You can't stand on them. They have no surface, no soil, no flag to plant. But they may be the most valuable invisible places in the solar system. They are where we learn, where we watch, where we build. Places where the forces of the cosmos balance just enough for us to rest. As we expand into space, our journey won't be made in straight lines. It will follow the curves and eddies of gravity, and the Lagrange points will guide us. These quiet nodes will serve as stepping stones, observation towers, gas stations, and eventually, homes. In the age of rockets, we chased speed. In the age of infrastructure, we'll chase stability.